Hello everyone. So let's solve this 8 code medium problem, largest magic square. So the problem states that we are given means a k cross k magic square is a k cross k grid which is filled with integers such that every row sum, every column sum, and both diagonal sum means the main diagonal as well as the anti-diagonal that we have. The integers means their sum should be all equal. Okay, and like they can like means the elements do not have to be distinct; they can be like duplicates as well. So simply like every 1 cross 1 grid will be a magic square only because the row sum will be that element only, the column sum will also be that element only, the main diagonal as well as the anti-diagonal will also be that single element only. Since 1 cross all 1 cross 1 squares will be valid trivially. Now we are given an m cross n integer grid. We need to return the size means the side length of the largest magic square that can be found within this grid. So we are given suppose we are given this grid. Okay, so now we need to find such a square means the largest size of a square. Suppose it is 2, so maybe it can be this square or this square or this square, such that it is a magic square means all the column sums all as well as all the row sums as well as the sum of the main diagonal and the anti-diagonal is the same. Okay, so let's see the given input. So suppose this was a given input, so in this the largest magic square that we can form is of size 3 cross 3, and we can see like the sum of this element is 12, this row is 12, here also the sum is 12, here also the sum is 12, as well as the column sums are all 12. And talking about the main diagonal, 5 plus 4 plus 3 is 12, and anti-diagonal sum is also 12. So as you can see, like all the sums of main row, column as well as main and anti-diagonals are same, hence this is a magic square. Okay, and since like this is a magic square and the largest size that we can get here is or what is this, which was our rather 3 cross 3, since the output for this case will be 3. Okay, similarly we have another input. So here we can see like the largest size that we can get is of 2 cross 2 where all elements are same, so hence all the row sums as well as all the column sums and the main and anti-diagonal are the same. Okay, so hence in this case the output will be 2. So what can be like the most brute force way of solving it? So like this problem is like pure implementation based problem. There is not much logic involved. We'll simply do what the question is asking us to do. So the question simply asks us to find this k, find the largest k. Okay, so maybe we can start from this k. Okay, we'll start from k. What is the maximum like size of a square possible? So it will be simply what? It will be like a minimum of n comma m. This will be the maximum size of any square possible. For example, here m is 3 and n is 4. So in this case, the maximum size that can of n square that can be formed is of order 3 cross 3. Okay, so this is the maximum size of a square that we can get in this grid. So we'll start from this maximum value and move on till like 1. Okay, so obviously like 1 will be the most trivial answer. This will always be possible. So we can like start from this value k equals to minimum of n comma m and move till the size of square 2. For one square we do not need to check because it will trivially be true only. Okay, so we simply start from this, and now what do we want? We'll check for all squares of size k cross k. Okay, the current k that we have. So suppose the current k, how do we find out all squares of size k cross k? So we know like the top left corner, if we fix it top left corner, suppose we want to find 3 cross 3 squares, so the 3 cross 3 will be fixed. Okay, if we fix the top left corner we will be able to get it. Now when another top left corner can be this. Okay, so these are the only two possibilities of the top left corner. So if you fix this top left corner r comma c, so we'll iterate through all possibilities of this r comma c for this k cross k, and then like we'll have the current square grid of k cross k. Then we'll find the row sums as well as the column sums as well as the main diagonal and the anti-diagonal sum, and if all of them are same, then we'll simply return this k as an integer as soon as we find a k, find a grid which satisfies. And since we have started from the large value only, so as soon as we are able to satisfy this requirement, we will be simply returning k. So let's analyze the complexity of this problem. So the k will be going from what? It will be going from a minimum of n comma m to 2. Okay, now we need to find this r comma c. So for finding this r comma c, this r will loop from what? From 0 till 0 till what? It will be moving till since m is the number of columns, so it will be moving till m minus k. Okay, so that means the maximum width that we get will be m minus k, plus k minus 1, that means m minus 1. Okay, so this like c will be moving from 0 till m minus 0 till m minus k, and c will be moving to 0 till n minus k. Okay, so r will be like simply downwards, and this will be upwards if m is the number of rows and n is the number of columns. Okay, so we can move these values. Now we have got a k cross k square, okay, based on this r comma c. So if this r comma c is fixed, then we'll be able to make this k cross k grid. Okay, now once we have got this k cross k grid, we need to find the row sums as well as the column sums, right, as well as the main diagonal and anti diagonal. So how do we find the row sums? So row sums will be simply for each row, for each I, from what r till what r plus k minus 1. Okay, and we will, for each I will be having the current row. Now we'll iterate for j's and find the sum. Okay, similarly we'll, to iterate through the columns, we'll be moving j from what, from c till c plus k minus 1, and we'll find the column sum in like by iterating through the row. Okay, so we'll be getting the sum, and as well as initially we can simply find the main diagonal sum. How we'll find it? So we means if this coordinate is r comma c, then it will be r plus 1 c plus 1, r plus 2 c plus 2, and simply till r plus k minus 1 c plus k minus 1. So we'll simply iterate for suppose x from 0 to k minus 1 and find the sum of what, r plus x comma c plus x. Okay, so this means we can find the sum of these values in the present at these grids, and then this will be suppose the initial sum that the target sum that we have. Then we can simply find the anti-diagonal sum. So anti-diagonal sum I will be able to find. So again we have r comma c. So this coordinate will be what? This coordinate will be r comma c plus what, k minus 1. Then this one will be r plus 1 comma c plus k minus 1 minus 1. So it will simply like we can again iterate for x from 0 till k minus 1, and this will be r plus x and c plus this k minus 1 minus x. So doing this coordinates will be telling the, means we will be able to get the elements in present in the anti-diagonal. Okay, and this will help us find the sum of the main diagonal, and we can simply iterate through each row as well as column to find the row sums and column sums. And if like we'll initially find this sum, okay, and then we'll find new sums and see like whether this sum is equals to this or not. As soon as it is not equal, then we can simply return false. Okay, so this is like the approach. So the time complexity of this will be simply, since k can grow up to minimum of n comma m, so it will be minimum of n comma m into, now we are finding this r comma c, it can go up to, look, we go of n into m. Okay, so it will be n into m. Now we have a k cross k grid, and the size of k will be can maximum to big of means minimum of n comma m. So it will be what, minimum of n comma m, and now we'll be iterating through the entire grid to like find this sum, row sum as well as column sum, right? So it will be minimum of n comma m square. Okay, so it will be like in the order of like big of n ki power 5, right? So let's see the constraints here. So n and m can go up to 50. Okay, so this will be simply 5 ki power 5 into 1e5. Okay, so it will be 125 into 625 into 125. So approximately of the order of 1e9, I would say. So this may like give us TLE here. So if the test cases are like strong, then because at each step we are taking minimum of n comma m, so if the test cases are strong, then it will give TLE, or maybe it gets accepted as well. But the complexity remains the same. It will be of the order of approximately big of n ki power 5. So I hope there's nothing logic involved in this. We simply try to follow what means we are required to do, and then we try to satisfy for the largest square size from k, and then move to the smaller. And then when we have this k cross k grid, we try to satisfy the requirements for this k cross grid and see whether we are able to get all the sum size equal or not. So let's see the implementation for this approach. So we'll have simply like this m and n are the number of rows and number of columns. Now we'll iterate for k from minimum of m comma n till 2. So greater than 1, because 1 is trivial. So if we do not get any k result as answer, then we simply return 1 in the end. Okay, now we iterate through all the possibilities of the r comma c that we have. Okay, so all the top left corner for each square of size k. Now we'll check whether this means with this starting point and of size k, whether this grid is a valid magic square or not. And if it is a valid magic square, then we simply return k. Now we need to see this function, how we'll be writing this function. So this function we first need the this r comma c is fixed. So now the first step is to find the main diagonal sum. So main diagonal sum was simply r plus x, c plus x, and x goes from 0 till k minus 1. Okay, now anti-diagonal sum will be r plus x and c plus k minus 1 minus x. Okay, now this anti-diagonal sum, if it is not equal to this target sum, then we simply return false at this step only. Now if it is equal, then we find the row sums as well as the column sums. So I will find the row sums, will iterate through each row and find the row sum for each row. And if this row sum is not equal to the target sum that we want, then we'll simply return false. Okay, and similarly we'll find the column sum, simply iterating through the columns and then finding the sum of each column, and then we'll be simply, if the column sum is not equal to target sum, then we'll return false, and if all the sums are equal, then in the end we'll simply return true. Okay, so this will be like the overall big of n to the power 5 approach that we have, and yeah, we have not used any space, so the space is constant here. So let's try to submit this code and see how much time, whether it gets accepted in the LeetCode or not, because like maybe it will get accepted, or maybe it will get TLE based on like whether test cases are strong or not. Okay, so let's try to submit it and see. So yeah, it runs fine, like it runs in 24 ms and beats 44% of solution. That means like test cases are not very strong. So this big of n to the power 5 approach works here, but means can we further optimize it, because this n to the power 5 was the worst that we can do, because this was like literally what the problem statement mentioned. We try to do that only. So can we like optimize it? So let's analyze this code here. So we saw like we'll definitely need to see for each square of size k. Okay, and we'll definitely need these starting points. Okay, starting means top left corner, so that we are able to see for a particular, means we'll definitely need to iterate through all like k squares, k cross k squares. Okay, and this k value can change according to this. Okay, so we'll definitely need to iterate through this. What we can optimize is, maybe we can optimize this is valid magic square function, because currently it is taking what it is taking, means this is taking a big of k, this is also taking big of k, but this is taking big of k square. Okay, as well as this is taking big of k square, which is making the overall complexity for this means is valid function as big of k square. So maybe if we are able to find this in big of k, maybe we try to find this in big of k as well, so that the overall complexity boils down to big of n to the power 4, okay, instead of n to the power 5. So can we do that? So we can simply know what do we need to find. We need to find the row sums. Okay, row sums for each row. Okay, and for finding that, what we are doing is we are simply iterating through all the elements and then finding the sum. And similarly for column sum, we are iterating through all the elements and then finding the sum. So can we do some pre-computations here to like find out this sum, to avoid this loop, avoid this internal loop that you said that is increasing complexity? So obviously we can simply like use prefix sums for this, right? Instead of finding out the sum for each row in like iterating through the elements, we can simply use prefix sums, and then we'll be able to do this in constant time, as well as we'll be able to find this column sum in constant time as well. So this is what we can do here, and simply we'll be able to like optimize from big of n to the power 5 to big of n to the power 4. So let's see this optimized code, means everything else will remain the same only. This like everything else remains the same. We just need to do this pre-computation. So we'll have these two prefix sums, row sum and column sum. So row sum of I means for ij will be simply row sum of I comma j minus 1 plus the value present at this grid. Okay, so grid of ij plus row sum of I comma j minus 1. If call sum, it will be simply call sum of ij will be call means grid of ij plus call sum of I minus 1, because it is the previous row. For this column it will be I minus 1 comma j. Okay, so we'll do that, and we'll maintain the indexes so that this j or I doesn't become negative. So we'll compute this prefix sums, and then everything else remains the same, means this function, this call remains the same. Now we'll be checking this magic function. So in this magic function, what we do, this part remains the same only, main diagonal and anti-diagonal sum. Now we will simply optimize, means here we are using a loop to iterate through all the elements. Now we are able to find the prefix sum of, so prefix sum of like from start to end is simply prefix of end minus prefix of start minus 1. Okay, so we'll be able to simply find the current sum that we have, and then we'll check whether it is equal or not, and simply we'll be able to find this column sum as well. It will be simply what the end row that we have and the start row that we have. So end row minus start row minus 1. So if its start row is greater than 0, then it will be start row minus 1, else it will be 0. Okay, so hence we will be able to do means this check in big of k, and hence the overall complexity of this means algorithm will be of the order of big of n to the power 4. So hence we can simply see like we are able to optimize from the brute force, means everything else remained the same. We simply tried to see whether we can optimize something, and we saw like we can simply, since we simply need to find the means sum of elements of each row or sum of elements of each column, so we can pre-compute that, and using prefixes we will be able to find it in constant time. So let's try to submit this code as well. Means this is the same code, but just we have done pre-computations, and now let's try to submit it. Initially it got accept ran in 24 ms. Now it should run like faster if the test cases are good. So yeah, it like it doesn't beat anything, because I think like test cases are not of like means 50 cross 50 grades are there, and suppose only k equals to 2 satisfies. So if suppose any test case is of that form, then I think like this will perform very fast. So yeah, this was like a better approach for this problem. So I hope you were able to like grasp the implementations of both the approaches. This was like simply an implementation based problem. There was nothing like core logic involved, or we need to do some derivations, nothing like that. So yeah, I hope you were able to follow along, and if you did, make sure to like as well as subscribe. And if you have any doubts remaining in like any of the topics, then make sure to comment down. I will be happy to respond. Thank you so much for watching.